Let's move to step 2 of the process. Let's collect the data and define the model. The first step is to make sure we understand what our random variable is, and as we said before, X will equal the number of sushi rolls demanded each day. This is the random variable. Now we don't know how it's distributed yet, but this is the thing that we want to vary, the uncertainty in the system. Now we're going to determine the relationship between the other various variables. So what do we know? We know that the S, or sales price, of each sushi roll is 80 SCR per roll. We know the cost of each is 25, and Q is the quantity that I want to make each day. So my policy is going to be Q. That's one of my inputs to the model, and I'm going to vary that X and see how well I perform. Now the revenue, the daily revenue, is going to be equal to that sales price, 80, times the minimum of either the amount that I make or the demand that day, min of Q comma X. So for example, if Q is 10, I make 10 rolls, and 8 people show up to order them, then my revenue is going to be 80 times 8, the minimum of 10 and 8. Similarly, suppose I make 8 rolls and 10 people show up for demand. What is my revenue going to be? The minimum of Q and X, 8 or 10, it's going to be 8 again, because I can't sell more than I make or more than the people who show up. And then finally, the cost is just simply the cost of each roll times Q, how much I'm making each day. The performance metrics kind of follow and use these variables. We'll look at daily profit, which is just revenue minus cost, and we'll look at unfilled demand and extra rolls. So unfilled demand, or stockouts, is going to be equal to the max of the demand minus the quantity made, or 0. So if you think about it this way, if I make 10 and sell 8, do I have unfilled demand? 10 minus 8, or excuse me, it'd be 8 minus 10 is negative 2 and 0, so therefore I would have no unfilled demand. However, if the situation is where I make 8 and the demand is 10, then it's going to be 10 minus 8, 2, versus 0, 2 is greater. So this is simply capturing how much demand I'm missing. The flip side of this is the extra rolls, and this is going to be the max of the quantity I make minus the demand. So, for example, if I make 10 and 8 people show up, the demand is 8, 10 minus 8 is 2. So what does that mean? I have 2 rolls that I didn't sell. That's the extra amount. So you can look for each day that one of these numbers will be 0 and one will be a positive integer, unless my Q exactly equals X that day. You will always either have unfilled demand or extra rolls at the end of the day, or it worked out perfectly, which will rarely happen. The last step here for step 2 is to collect the data and estimate the probability distribution of our random variables. And so there's a bunch of different ways you can do this. So the first case is where you don't have any sample data. Let's say you're trying to simulate something, but they don't have any history. So what you can do here is talk to experts. Try to understand the worst, best case, and most likely. This is where that triangle distribution comes in so handy. And if they can't come up with a most likely value, then stick with the uniform, worst case, best case. So what you're doing here is you're trying to say, okay, what's the best, most reasonable distribution I can use, given that I have no sample data, no history. If you do have sample data, then take that data, make histograms, look at those, calculate the summary statistics, and you want to conduct a chi-square test to see does it fit a traditional distribution, such as normal, Poisson, exponential. What we'll do in a second is we'll see if our data, our sample data, fits a normal distribution. Alternatively, you could go with what's known as an empirical distribution, and this is the actual demand from that sample. You have to be very careful here because, as we know from our previous lectures, the sampling will be different each time from a population, and so you don't want to overfit. You can use discrete empirical distributions. I've used these in the past when it makes sense, or you can do continuous, and you just have to assume that it's uniform within these ranges that you set. When at all possible, you should try to fit them to a traditional distribution, because then you can make assumptions on what the population distribution looks like.